First order means ready.
Yes.
Yes. Second order sufficient condition.
But this is necessary sufficient for in general.
It doesn't have to be differential.
It doesn't have, yes,
It doesn't have to be differential.
So
I
it
want to
could
be
be
differential.
but it could be different. But it still applies for any case, right?
This applies for any function. Yes.
So if you mention this, I mean, this is sufficient and necessary.
This is not really the first order. You have to look at the summary sequence of first order. Yeah, that's what it says. First order means generally greater, second order means this. Okay, so while it's loading, let's use the document camera. Okay. Before I start the next topic, numerical methods, so we are at the halfway mark of the course in terms of syllabus. From now on, we'll be looking at the numerical methods for solving optimization problem. Before I start the numerical methods, I just want to give you some examples of convex optimization problems. Because we have looked at ways of solving convex optimization problem, and to give you some idea where these kind of problems appear. So let's first, you don't need to take this down, I'll upload it later on, just to go through some examples, convex optimization, because these days many of the harder problems are formulated as convex problem. In the past, a lot of the problems were formulated as linear problems, okay? Because those problems can easily be solved. Now we can solve broad classes of convex problems, so the practical problems are formulated as convex problems. So let's first start with the linear programming problem. It's an optimization problem consisting of minimizing a linear objective function subject to linear equalities and inequalities. So in this course, we focused on minimizing a nonlinear function subject to nonlinear equality and inequality. So that's more general class of problem than the linear problem. So here, we're minimizing a linear expression, C transpose X, and also you have an inequality constraint. It's given in matrix form, so that we have finitely many linear equality constraints. So they are fine functions, and also inequality, and the finitely many equality constraints. So there is a matrix M by N. So they have an M equality constraint, number of variables is N, and so on, okay? So this is, of course, a special case of convex optimization problem because all the functions involved are affine functions, both convex and concave. So very special class of convex optimization problem. And you see that you are not only minimizing a convex function, you're also minimizing a concave function as well. So we know that solution occurs at the extreme points. So this is how linear programming problems are solved by going through the extreme points to find the minimizer. That's why the simplex method was developed. And although the class of LP, linear programming problem, seems to be quite restricted because of the linear objective and constraint, but it actually covers a huge class of practical problem in application and has a great impact. So a lot of the scheduling problem, the integer restriction here, they are used in various areas in airlines and industries and so on, lots of application, and they can be easily solved. So another modern example of a convex optimization problem you would have heard in recent years in data mining and machine learning, because the data are hugely available these days in various areas. So we want to make use of the data to predict things and solve part of the problem. So I want to give you a very typical convex optimization appears in machine learning. It's called the data classification problem. I'll show you how that problem can be set up as a convex optimization problem. Okay? So let's look at, suppose we are given two types of data. That means two types of points in Rn, say type A and type B. Okay? So type A points are given, say, x1, x2 up to xm in Rn. And type B is another set of points, xm plus 1 to xm plus p. Okay? So if you draw a little picture there, you have a collection of data. This is one type of data. There's another type of data. This kind of problem appears in lots of applications. You know, it can be if you look at the cancer data set, so this data can be benign cancer, else one is malignant cancer. So you want to distinguish that, use that to predict a new patient come in, whether the person is going to have got a certain treatment or not. On the other hand, in banking sector, you know, you have information about customers, good customers, and people had a bad record, and they can decide whether they want to recommend a home loan for these people or something. So they use this kind of data classification idea to make decisions. Okay, so the question here, so the figure here describes, say, the two sets of points. Say type A points are denoted by, say, asterisk there. So type B points are denoted by diamonds. Okay. The objective is to find a linear separator which separate these 2 points. So you want to draw a line, and one type A is one side of the line, the type B is on the other side of the line. Okay? How do you do that? There are infinitely many lines you can draw from there. You can draw lines here, here, and so on. So what's the best line which separates separate these points? Okay? So the objective is to find a linear separator which is a hyperplane in general of the form x is in Rn, W transpose x plus beta equal to 0. So in a 2-dimensional case, that's a straight line. In 3-dimensional case, it's a plane. So this is general. In Rn, so your objective is to find a linear separator which is a hyperplane of the form for which type A and type B points are in its opposite sides. Okay? So as I said before, the problem is not well defined in the sense that, so that means in one side, type A and type B points are in the opposite side, means W transpose x plus beta strictly less than one side and strictly bigger than one other side, because that's equal to 0 is the hyperplane, right? The points in the one side is strictly less than 0, other side is strictly bigger than 0. So that means we should assume that this system has a solution. So the one in one side, other one in the other side, right? So that's our basic assumption. So because sometimes you won't be able to find a linear separator as well, okay? So our assumption is that the 2 sets of points are linearly separable, meaning this system of inequalities has solution, okay? All right, so that the problem is not well defined in the sense that there are many linear separators, okay? So what we seek is, in fact, a separator that is, in a sense, as farthest as possible from all these points. You want to separate it as farthest as point from these points here. So how do we? So we want to define this problem in a sense that we can separate it. Okay. So let me give you what I mean here. So at this point, we need to define the notion of the margin of the separator, which is the distance of the separator from the closest point. So for example, here. So that's the margin. So that's this line, that's the closest point. So that's the margin. So obviously, you want to find a separator with a big margin, right? Okay. So the question is, how to find this margin first? We did that actually in the last lecture on the shortest distance problem. Okay. So the separation problem will consist of finding the separator with the largest margin. Okay. So to compute the margin, we need to have the formula for the distance between a point to the hyperplane. So how do you find this? In general, any point outside this plane, you want to find the shortest distance, which I did yesterday. You may not have focused on that. You were thinking about the class test, I guess. That was actually given the last year's final exam question. Okay? So let me show you that calculation. The shortest distance, we showed last time. So this is the exam. This is the question I went through in the last class before the test, the past exam question. So that gives you square of the distance subject to A transpose x minus B equal to 0. That's the hyperplane. Okay? So that gives you the minimum value of the distance. That's the square of the shortest distance from point D to A transpose xB, A transpose x minus. So we use it as a convex optimization problem. We find the global minimizer, and then the next question is the shortest distance to D from the hyperplane. So that's the one we're going to use for the separation theorem. Okay? So here's the answer to that question. So that if you have a hyperplane, A transpose X equals B, and D is a vector outside the plane, the distance between, so that gives you the margin, okay? The distance between D and the hyperplane is given by absolute value A transpose D minus B over norm of A. So this we calculated last time. So that gives you the margin. So now we can set the problem up. So we conclude that the margin corresponding to the hyperplane HB is, there are finitely many points there. You take the distance, take the minimum of that. That's the closest to the point, right? So that gives you, here's the problem then. The problem that we consider, you want a maximum margin, so that gives you the minimum margin from the closest, the margin from the closest point. Take the minimum, and then the separator. One set of points is one side of the hyperplane, another set of points is the other side of the hyperplane. So you want to find the hyperplane W and beta, satisfy this condition. But it looks pretty hard to solve, right? Because you want to minimize that, and then you have this affine inequalities. And also we have a strict inequality as well. So we want to reformulate it and try and get a convex problem so that we can solve it, right? Okay. I mean, this is how the practical problem set up and then solved. There's no point in having this because you have no idea how to solve this, right? Not only you want to solve it, you want to solve it very efficiently. Okay? So what we're going to do is to reformulate this. So I say that it's rather a bad formulation because it's not a convex problem, cannot be easily handled. Okay? So the objective now is to find a convex reformulation of the problem. Okay? So what we're going to do here, because of this affine nature of this function, if W beta is an optimal solution for this problem, then any multiple, alpha times omega plus alpha times B, is also the solution. You can easily say that it's all homogeneous there. So you can set that the minimum is equal to 1. So if it is, if it's not 1, you can divide by that and make it into 1. So that's a scalarizing idea. So therefore, that problem now simplifies to maximum. So that's 1. If you go back and look at the previous one, so you put this one is 1. So you get the problem 1 over norm, 1 over norm of W, and that restriction is put in there, and then you have this condition. Still, it's not a convex problem, and you see that the maximizing 1 omega is the same as minimizing omega squared. Simple calculation. So this is actually equivalent to minimizing half of, the half is put in just for convenience, you can drop the half, norm of W squared, and this minimum equal to 1, and this is less than equal to minus 1 and bigger than equal to 1. From this, you can show that, I have it written down here, how this is equivalent or written as in this form. Okay, so maximizing 1 on omega is the same as minimizing omega squared. Why? If 1 of omega star is the maximum, that's the same as, looks not usual. For example, so if 1 under omega is the maximum, so that means it's bigger than or equal to 1 omega 4 or omega, right? That's the maximum. So you multiply this, right? Omega is bigger than or equal to omega star, right? Take the square. So that's the minimum. So maximizing 1 on omega is the same as minimizing omega squared. Okay? So you reduce this problem into this form. So now you got a close to a convex problem. You have a quadratic function there. As a convex function, you have a affine equality constraints. The only problem is you still this unusual constraint sitting in there. Actually, you can drop that and show that the optimal solution that will be satisfied. So finally, we'll remove the problematic min equality constraint and obtain the convex reformulation. So this is the convex reformulation. A lot of the application in data mining, this is the one people use. It's maximum margin classification to separate the data. And this can be efficiently solved as a convex optimization problem. Okay? So that's how in many, yeah?
Why can't we just remove the definition?
Yeah, right, justification, yeah. Here's the justification, so how you can remove it. Okay. So from the previous constraint, you see that that will always bigger than or equal to 1 because of the constraint here. The removal that's justified, any feasible solution of the previous problem here should satisfy this, okay? And then at the minimizer, if WB is a minimizer, then it cannot be strictly bigger than 0. It has to be equal to 1. You can show that, just elementary calculation, okay? So that's how most of the application, this maximum margin classification is used. It's nowadays used in, a lot of biological problem, in finance, and one of the popularity of data science. This is the basic idea of optimization often used there. Okay. So that shows you how practical problem have to be reformulated in a form which you can solve, right? Just to finish up one more class of problem, which commonly used the portfolio selection problem. It's also a convex optimization problem. It appears in finance and management science quite a lot. Suppose that an investor wishes to construct a portfolio out of n given assets, numbers from 1 to n. Obviously, they are risky assets. You want to minimize the risk. There are several formulations to this. I'm going to look at the Markowitz model. This has this form, minimum X transpose Cx. So that's C is a covariance matrix. Some of you might have seen statistics. So that gives you the objective function that represents the risk. You want to minimize the risk. At the same time, you want to maintain a certain level of return. Alpha is the minimum return you want. That gives you the expected return. And this weight is equal to 1. So that's the portfolio problem. What's interesting here, the covariance matrix always positive semi-definite. So that makes the objective function is convex. So that's a convex optimization problem. It can be easily solved as well. Okay, so that's common in finance and so on. And the variance of portfolio, by the way, there will be a bigger question in the assignment on portfolio selection problem. You have to set it up and solve it. Okay, so I don't want to give too much details here. That will be given in the assignment. Okay, so just to give you some idea of where these kind of problems appear and how you can set it up, how you can solve. All right, now you know how to find the solution analytically. Now we want to look at numerical methods and computational methods to solving that. Okay, let me give you, start the next topic. Okay. So basically, we have covered the theoretical aspects of that, constraint optimization, and now we're going to look at different methods, that means numerical methods, for solving problem, that means iterative methods. Most of the methods in optimization are iterative methods. Look at the rate of convergence, and descent methods, line search, and model algorithm, and steepest descent method. The first method we're going to look at is steepest descent method. the question you want to ask, you know how to solve optimization problems. So why do we need to look at another numerical methods? You know the Lagrange multiplier method to solve it, right? Exactly. So let me give you a one variable example, see what we can do. Let's see if we can solve this or not. It's a calculus question. High school. This is the high school question. You asked to find the minimizer of x squared minus sin x. Okay? So let's calculate this. So let the objective function here, let fx is x squared minus sin x. One variable, x is in R. So what do we do? You differentiate it, make it equal to 0, right? Okay. Then f prime x is 2x minus cosine x. Make that equal to 0. And that gives you, okay. And then look at the second derivative. What's the second derivative? 2 plus sin x. What do you know about the second derivative? This is always positive, right? The sin x is between minus 1 to 1. So 2 plus sin x must be positive for all x. For all x is in R. So therefore function is convex, right? Okay. So f is a convex function. You have done the class test. So every stationary point is a global minimizer, right? So it has a global minimizer. What's the global minimizer? You need to find a stationary point, right? So you want to solve 2x equals cosine x. So what's the solution? You cannot find the exact solution for this, right? But we know that the solution will be a global minimizer. So what does it mean? You don't know how to find the solution, or doesn't have a solution? What do you think? Does it have a solution? Does it have a stationary point? Yes? But we don't know how to find it, right? So why do you think it has a stationary point? Let's sketch the graph. Okay? So that's y equals 2x. So y equals cosine x, something like this. So that's y equals cosine x, 0. So y equals 2x is something like this. Okay? That's the intersection. So that's the solution. So it has a minimizer, but we cannot find the exact solution. It does have a solution. So how do you find it? So you go to find the iterative method to find it. You can only find an approximate solution. No way of finding exact solution. So mathematics is not there to do that. So the question you're going to ask, how to find a solution? So x equals cosine x on 2. So this requires a numerical method, iterative method. This is actually solved using fixed point iteration. I'll show you later on how that point is found. Iterative method, start from an arbitrary point. Because you have no idea where that point is, start from an arbitrary point, trying to get close to the point. So we use the iterative scheme, xk plus 1 is cosine xk on 2, starting from xk1. You find the second point, x2 and x3 and so on. We can show that as k gets bigger and bigger, xk gets closer to that, the minimizer, x star, right? So that's called the fixed point iteration. We can show that that actually converges to the point x star. All right, so that shows that, for some problem, analytical method wouldn't work, or Lagrange multiplier wouldn't work. You have to use some approximation techniques to do that. Most of the practical problems are done like this, using iterative methods. Okay, so we're going to look at now the basic ideas of the iterative methods. And on this section okay, situate with the majority of the numerical methods or algorithms optimizations are iterative methods. That means you start from an initial point, then you improve that point, x1 to x2 and x3 and so on. As k gets larger and larger, you get closer to the solution. So this requires a starting point, initial guess, x node, and generate a sequence of point xk, which progress steadily towards a neighborhood of a local minimizer, then hopefully converges rapidly to the point x star. So that's how the scheme works. Start from the initial guess, you have no idea where the solution is, try to improve the solution, and get closer to the neighborhood of x star, and then it should converge quickly to the point x star if it works well. So the couple of definitions. The globally convergent means the starting point can be arbitrary. So iterative method is globally convergent, means given any starting point, x node, the method generates a sequence of approximate xk, which converges to x star. It's nothing to do with the global minimizer, by the way. Global convergent means the starting point is arbitrary. We'll see later on, many of the methods, the starting point has to be closer to the minimizer, otherwise it wouldn't get to the solution. Okay? But globally convergent means you can start at any starting point and then generate the sequence xk and converges to x star. Here's the warning. The global convergent does not imply x star is a global minimizer. Okay, so the terminology is confusing. Global refers to the fact that the starting point is arbitrary. Okay, so we will be looking at several methods, approximation method, which finds the minimizer, iterative method. So we want to know, we have seen in calculus, right, you have a sequence xk, and you find the limit, right, xk goes to the point x star. You don't often look at how quickly that gets to the limit, right? We want to look at that here, because otherwise, then only you can compare two different methods, how quickly the method converges to the solution, okay? So that comes to the idea of rates of convergence. The rate of convergence means, before I give you the definition, let me show you the reason. So an effective technique for judging a rate of convergence is to compare the improvement at each step to the improvement at the previous step. So you had the one stage, you see the improvement of that step to the previous step. So in other words, you measure the closeness of xk plus to x star related to the closeness from the previous point xk to x star. So that's how you judge the improvement there. So we're going to come up with a definition to look at the rate of convergence. Here's the definitions. Suppose that xk converges to the point x star. The limit point is x star. If xk node is x node for some finite number k node, then we say that's finite convergence. Generally, you have an asymptotic convergence. It takes infinitely many k. If xk node is equal to x star for some number k node, then we say the xk converges to x star in finite steps. In other words, you have a finite convergence. We don't often have that finite convergence. Some problems, yes, you have. It reaches to the solution in finite steps. So in generally, you have an asymptotic property. So xk is not equal to x star for all k. And this tells you we are comparing the closeness xk plus 1 to x star to xk minus x star. Now look at the ratio. Alpha and beta number I'll show you in a minute here. Generally, alpha is 1 or 2. Okay? So obviously, the beta, the limit is always bigger than or equal to 0. Why? Because norm is always bigger than or equal to 0. So the whole sequence is always non-negative, right? So limit is also non-negative. So the beta is generally non-negative. So we want to get as a finite beta. So the rate of convergence of xk is called linear rate of convergence, means alpha equals 1 and beta less than 1 and bigger than or equal to 0. The beta has to be, limit has to be less than 1 if it's going to converge, right? The improvement from the k plus 1 decay should be smaller than that. So xk plus 1 minus x star is generally smaller than xk minus x star if it's going to converge. So beta has to be less than 1, and obviously bigger than or equal to 0. If alpha equals 1, it's a linear first order convergence. If alpha equals 1, beta equals 0, it's called superlinear convergence, slightly faster than the linear convergence, because the convergence ratio beta is small here. Beta is 0. And the faster convergence is called order 2 convergence. Quadratic convergence means alpha equals 2. You compare with the square of the previous distance at converges to be beta. So this is called the second order rate of convergence. These are first order rate of convergence. So linear convergence means alpha equals 1, beta bigger than or equal to 0. Superlinear convergence means alpha equals 1 and beta equals 0. And quadratic convergence means alpha equals to 2. We need to look at some examples to do that. There's a couple of remarks here. The quadratic convergence is known as the second order convergence because alpha is 2. And for linear convergence, convergence ratio beta is important. So quadratic convergence implies superlinear convergence implies linear convergence. So that's the faster rate of convergence. That implies superlinear convergence. That implies linear. Why is that? Is it clear from the definition? Can you say from the definition here, linear convergence, superlinear convergence implies, quadratic convergence implies superlinear convergence implies linear from here? This means this is true for alpha equals 2, right? Can you show that should be true for alpha equals 1? How do you do that? So quadratic convergence implies superlinear convergence, implies linear, just follows from the definition. So how do we establish that? Quadratic convergence, it's easy to see from the definition superlinear convergence implies linear convergence because the only thing is beta equals 0, right? Other one is true for any beta. So that is obvious. So to show that quadratic convergence implies superlinear convergence, all right, you want to look at this ratio, right? Alpha equals 1. Xk plus 1 minus x star over xk minus x star. So what I do, I multiply top and bottom by xk minus x star. Then you get here xk minus theta squared, get xk plus 1 minus, it should be xk, right? This is xk. You multiply by xk minus x star, top and bottom. So what happens here? Because quadratic convergence, this has a limit. Okay, this goes to beta. And what happens to this? That goes to 0, right? Xk goes to x star, so that goes to 0. So the whole thing goes to 0. So that's our superlinear convergence. This is xk. Xk plus 1, so that goes to beta because the quadratic convergence, and xk minus x star goes to 0. Therefore, the whole thing, that goes to 0, and this goes to beta, the whole thing goes to 0. So that means the convergence ratio of beta equals 0, that's superlinear convergence. So that's how that implication follows. This is immediate, superlinear convergence, linear convergence immediate from the definition. So if you look at the definition there, that is straightforward. See, if alpha equals 1 and beta equals 0 is a particular case of this. So obviously, this implies this, right? So we just shown that this implies this. So that's a faster rate of convergence. The slide is slow, right? And the good numerical methods, iterative methods, should have at least superlinear convergence. Linear convergence is not very good. you could see from examples from this so that's a norm. So the rate of convergence is an asymptotic property, but still gives you some information of how quickly xk converges to x star once xk is closer to x star. So it's a limiting property, right? So when xk gets closer to x star, we want to know how quickly it converges to the solution we want. And then you can distinguish various algorithms from the rate of convergence. Here's an example. Maybe I'll give you some. So this one here, that's a linear convergence. Can you see the colors there? So this one, alpha equals 1, a linear rate of, so there's no, that gives you the error. That gives you the number of iterations. See, as it number of iterations increases, there's no change in the error. Almost, it's flat, almost the same. It's not good. So this one is, the green one here, so that's a linear convergence, but the error decreases in a linear rate, okay, as it increases here. So this one, the red one is a superlinear convergence, converges, the error rate decreases faster here, come down here. So that's the quadratic rate of convergence, okay, and the error sharply decreases. Okay, I think it's not, the numbers not right there. Okay. All right, let's look at some simple examples to calculate the rate of convergence. So start with a simple example, just to give you the rate of convergence of sequence. So say 1 on 10 to the k. Obviously, limit is 0, right? As k gets bigger and bigger, 1 on 10 to the k gets smaller and smaller, goes to 0. So limit is 0. So we want to know how quickly it converges to 0. Okay. So let's compare. This is a real sequence: xk plus 1 minus x star to xk minus x star. Okay. So alpha equals 1. I'm going to show this linear. So that's 110 to the k plus 1 minus limit is 0 over 110 to the k minus 0. Okay, so all positive numbers. So that's 110 to the k plus 1 over 110 to the k, which is 1/10. So obviously the limit is also 1/10. Okay, so limit as k goes to infinity, xk plus 1 minus x star over xk minus x star equals 1/10. That's your beta there. So it converges linearly. So, and xk converges linearly to x star, this is 0. So linear rate of convergence is linear. You can show that if we take the square, it won't have a limit. Okay. So let's look at another example. Xk equals 1 on k factorial. Again, the limit is 0, right? So as k gets bigger and bigger, 1 on k factorial gets smaller and smaller. It goes to 0 as k goes to infinity. So limit is 0. Okay. So let's calculate the ratio xk plus 1 minus x star over xk minus x star. Okay. So that gives you 1 on k plus 1 factorial. X star is 0 over 1 on k factorial minus 0. Again, these are all non-negative numbers. So 1 over k plus 1 factorial over 1 over k factorial. So that's 1 over k plus 1 factorial times k factorial, right? So k plus 1 factorial can be written as k plus 1 times k factorial, right? So times k factorial. K plus 1 factorial means k plus 1, k minus 1, and so on. So you have this. So that gives you 1 over k plus 1. So as k goes to infinity, equals limit of 1k plus 1, which is 0. So beta is 0, it's a superlinear convergence. So in fact, you need to show that when you square it, it doesn't converge to a point. So slightly faster than the previous case. 1 and 10 to the k decreases slowly. 1 and k factorial decreases faster, okay, to 0. Have a look at the third example. Uh, 110 to the 2 to the k. Okay, again, as k goes to infinity, what happens? As k goes to infinity, x to the k, I don't know, this has to be done there. Yes? After this. Yes? Again, it goes to 0, right? At 0. So let's look at xk plus 1. You want to show that it's a faster rate of convergence. Xk minus x star squared, right? So that gives you 1 on 10 to the power 2 to the k minus 0, 4 plus 1, 2 to the k minus 0 squared. So what do we get here? 1 on 10 to the 2 to the k plus 1 over 1 on 10, that's positive, right? 1 on 10 to the 2 to the k times 1 on 10 to the 2 to the k square, right? So that is 1 on 10 to the power 2 to the k plus 1. So 1 on 10 to the power 2 times 2 to the k, right? 2 times 2 to the k. So that's 2 to the k plus 1. So that goes to 1 as k goes to infinity. So that goes to, that has a super linear convergence, it's a quadratic convergence. That implies super linear conversion as well. X star. In the previous case, you can actually calculate this. If you look at the square of this, you will find if you look at the square of that, it wouldn't converge to a finite number. You can calculate this. So 1 over k plus 1 factorial over 1 over k factorial squared, right? If you do that, so you get 1 over k plus 1 factorial times k factorial times k factorial. So that goes to 1 over k plus 1 times k factorial. So that goes to 0, that goes to infinity as k goes to infinity. So it's not quadratic convergence, it has superlinear convergence. We can have a break for a minute, and then we look at iterative methods. Okay. You can see that how fast the numbers decreases to 0 from those numbers there. Yes?
The summation. I can see this, yeah. So it's right. Doesn't really specify that this is the first order sufficient and the second.
Yeah, the first order means that it is graded.
Yeah.
That's what it means. Second order substitution means what?
It means second, yeah.
Yeah.
But if you said this, then that is correct as well, right? I mean, it's not wrong.
You can use that to prove that as well in the question. You can use that, or you can use
Yeah,
this to prove
but the first part said state the first order sufficient necessary conditions.
Yeah, it's all right.
Okay. Okay. I used it for like the second part. But okay.
Yeah, I mean, yeah.
I have a question about this one. Can I solve the problem, find the solution, and use the Taylor series?
It's again approximation.
Yeah, to get a approximation, yeah.
Yeah, that's what. Fixed point is one method like this, is another approximation. Yeah, various iterative methods can be used to find the solution. I'll show you later on today. Another method, the fixed point iteration. Yeah, this is a Fourier series iteration. Yeah, that's a solution for cosine x.
And of this one, how can you get for the alpha equals to the projective convergence? You can get that this one.
Yeah, so
The superline.
Here. See? So you won't show that this goes to the limit, right?
Yeah.
That's the alpha 1. So you can multiply top and bottom by xk minus x star,
Yeah.
a square,
Yeah.
and this.
Yeah.
So this quadratic convergence means this goes to limit,
Beta.
beta.
Yeah.
This always goes to 0. Xk goes to x.
Why this, of course, is
The xk converges to x star. That's the limit.
No, we don't know because this said that.
No, the x star is the limit point of xk. You know, xk converges to x star. So the distance is 0. Xk goes to x star. By definition, xk no x goes to 0.
Oh, this is by the assumption of that.
By the
X star
assumption.
is the limit of
Yeah,
X.
you got to know the limit. So that goes to 0.
Hey, is it a quotient sequence?
Cauchy sequence, yeah.
It is
Limiting sequence of Cauchy sequence as well. Yeah.
Oh,
So the Cauchy sequence is actually used for for example, why the beta has to be less than 1. See, if it converges, say if xk converges to x star, right? So the xk plus, for large values, okay, xk plus 1 minus x star should be smaller than xk minus x star, right?
yes.
Then only it will converge. Okay, so when you divide that, the limit should be less than equal to less than 1. Yeah, it should be. So that's less than 1. So that implies 2 because of the square. And this is obviously implies that.
I see. Thank you.
Yeah. You can use that also for that as well. From that also you can this one. Yeah, you can. Okay. A couple of more examples. All right, take a look at this example here. You ask to calculate the rate of convergence, the sequence xk, 1 on k to the power k. Okay? So, again, as k goes to infinity, so k to the k gets bigger and bigger. So 1 on k to the k, smaller and smaller, goes to 0. K is a natural number. So, as k goes to infinity, xk, 1 on k to the k, goes to 0. So that's x star. Limit is still 0. Okay. So we want to know how fast it converges to x star. So we look at xk plus 1 minus x star 2 xk minus x star. This is a real sequence, so the norm is an absolute value. Okay, so that gives you 1 over, replace k by k plus 1 to the power k plus 1 minus 0 over 1 over k to the power k minus 0. Okay, you can drop the absolute value into positive numbers. K to the power k. So that gives you 1 over k plus 1 to k plus 1 to the power k to the power k. So what's the limit? So let's simplify this. You can put here, take factor out 1k plus 1. So that's factor out 1k plus 1. So you have k to the power k over k plus 1 to the power k, right? Out of the k plus 1, power factor out 1k plus 1. So that gives you this. So 1 over k plus 1. So this one is k over k plus 1 to the power k. What's the limit? What's the limit of that as k goes to infinity? K over k plus 1 to the power k. Let's do one more simplification. Divide the top and bottom by k. 1 over 1 plus 1 on k to the power k, right? 1 over 1 on k to the power k. So that gives you xk minus x star plus 1 over k plus 1 times 1 over 1 plus 1 on k to the power k. You would have seen the limit xk plus 1 minus x star over xk minus x star as k goes to infinity. The limit 1 over 1k plus 1 and 1 over limit 1 plus 1 over k to the power k. What's the limit of this? That goes to e. Remember, you use the log rule and L'Hopital's rule and so on. You wouldn't have missed it in calculus. You would have seen that goes to e. Okay? So that goes to 0, that goes to e, so that goes to 0. So that converges at a superlinear rate. So xk 1 over k to the k converges superlinearly to 0. Okay, so that's how you calculate the rate of convergence. There's another example there. On the slide. If you look at c to the power 2 to the k, c is a number between 0 and 1. So you can think of c as a fraction. So as k gets bigger and bigger, the fraction gets smaller and smaller when you have a power. 2 to the k increases, the fraction gets smaller. The limit is 0. Okay? So if you look at the ratio with alpha equals 2, xk plus 1 minus x star over xk minus x star squared, it's x2k plus c2 to the k plus 1, c2 to the k squared. So that is c2 to the k times c2 to the k, 2 times 2 to the k, that's 2 to the k plus 1. So that gives you 1. Okay? So that converges at a faster rate. The limit is 1. It's a quadratic rate of convergence here. Okay, I just want to go back to that first example. We looked at x squared minus sin x. We have the problem of finding the solution for this equation, x equals cosine x and 2. We couldn't find the exact solution. Graphically, we have shown that it has a solution. Now we're going to find approximate solution. That's all we can do. Cannot find exact solution. So I said about the fixed point iterative scheme. So that's the fixed point iterative scheme. We start from an arbitrary point x1, okay? And the other point is xk plus 1 is cosine xk on 2. Just So the x2 is cosine x1 over 2. x3 is cosine x2 over 2, and so on. K1, 2. And we call it, say, phi x is cosine x. Let's call this function phi x is cosine x on 2, right? That means phi xk means cosine xk on 2. Okay. This is an arbitrary starting point. We are iterating, and we want to know it converges or not, right? Starting point is arbitrary. You can start from anywhere. We know that the intersection is somewhere closer. Okay, so we know that solution exists. We have shown graphically x equal cosine x2 has a solution. So that means the solution x star equals phi x star, right? So x star equals cosine x star on 2 at the solution, which is x star equals phi x star. Okay, so let's look at this. We want to show that this sequence converges globally to the point x star. That means starting point is arbitrary. I'm going to show that the global convergence here. You see how the calculus can be used to this convergence. Okay, so let's look at the ratio. Xk plus 1 minus x star over xk minus x star, right? So from a definition, xk plus 1 phi xk. That's how iteratively did that. And we know x star is phi x star. X star is the solution. So x star should be equal to phi x star. Phi xk minus phi x star over divided by xk minus x star. Okay? Phi xk minus phi x star, remember the mean value theorem? What's the mean value theorem? You remember the first year calculation, the mean value theorem? Let me remind you, get a piece of paper. Phi xk minus phi x star over divided by xk minus x star is the derivative. Remember that go back to the document camera for a minute. So if you have a function, you have a function, you have a 2 point here, you have any 2 points here, phi x2, phi x1, that's the graph, say, fx. What's the mean value theorem? Fx minus fb minus fx minus fa over x minus a equals f prime c for some number. So that means you can find a point here, and the slope is the same. This gives you the slope. That's mean value theorem. The derivative at the point. You can always find a point on the curve. The tangent is parallel to that chord. So that is that the mean value theorem. So that's actually used here. So that means here, phi xk minus phi x star divided by xk minus x star equals the slope, phi prime ak. Ak is a number between xk and x star in the interval there. This is a real function, right? So the mean value theorem, you have this. And phi x is cosine x and 2. So phi x, so that cancels out, right? So you get phi prime xk is sine a equal to 2. Phi x is cosine x on 2. Phi x is minus sine ak on 2. You get the absolute value, sine ak on 2. But sine is always less than or equal to 1, right? So that gives you less than or equal to half. So that is bounded by half. So that means you have, when you multiply this, xk plus 1 minus x star is half time xk minus x star. So xk plus 1 minus x star is half time the previous distance, xk minus x star. And you apply it again, this is half time the previous one, xk minus 1. So half squared times k minus 1. And repeatedly you get half to the k times x1 minus x star, right? So x1 is a given point, so that's a constant. As k goes to infinity, what happens half to the k? That goes to 0. So that goes to 0, therefore this goes to 0. Okay? As k goes to infinity, xk plus 1 minus x star goes to 0, because this one goes to 0. the whole thing 0, then it's smaller than that goes to 0 as well. So that gives you hk plus or minus x star goes to 0. So that means it converges to x star, at least linear, and you can show that the convergence ratio is less than half. It's k minus x star sin ak and 2 as k goes to infinity. Ak goes to x star. Ak is between xk and xk minus 1. So sin ak go to sin x star. So sin x star is less than 1. So that's between 0 and half. So that actually globally converges to that point. So even though you have no idea where the point is, you can start anywhere that iteratively get very close to that point from the fixed point. So that's a globally convergent iterative scheme, but it actually converges slowly, the linear rate of convergence. Alpha equals 1. Okay? Slow rate of convergence, but still it converges. Okay. So using this basic idea, now we're going to look at the methods for unconstrained optimization problem. So why are we going to start unconstrained optimization? Because most of the practical problems are constrained problems. But I'm going to look at methods for unconstrained optimization problem first. We will see later on, when you solve a constrained problem, at each step you have to solve an unconstrained problem. So it is important that we should be able to solve unconstrained minimization problem very efficiently. So that's what we're going to look at here. First, iterative methods for solving unconstrained problem. So though the many real-life problems involve constraint, the methods used to solve them are heavily based on iterative methods for unconstrained problem. So at each step, you will be solving unconstrained problem. In fact, you will see later on, at each step, you will be solving unconstrained problem in one variable, in many cases. Okay? In this section, we are going to look at iterative methods that are used to find the local solution of fxr. So mostly local solution. Very hard to find the global solution in the nonlinear situation. So we will try and find iterative methods to find the local minimizer, or at least a stationary point. So here's the fundamental underlying structure for almost all iterative methods for optimization problem. Let me give you that. So what happens here, you start at one point. Okay. So as you have seen in the previous example, you want to find that's your minimizer, x star, say. Okay? You start somewhere. That's your starting point. We want to get to that point. The idea is to first, you look at the function value. You are minimizing a function, right? You are minimizing a function x is in Rn. So that means, so if it is not a minimizer, or you can check the gradient and say gradient is not equal to 0, it can't be a minimizer. So you need to improve the point, right? So from this, you want to find a direction where function value, so we are minimizing, function value should decrease, right? So this is not a minimizer. We want to find a better point. The function value will decrease. So we move in this direction. We know that function value decrease. We'll find some rules which tells you that in this direction function value will decrease. So we move along this direction. Then we want to know how far you can move in that direction while reducing the function value. So you can move. Okay, that's all you can move while minimizing the function value. If you move further, function value may not decrease. You stop there. You find a new direction where function value decrease. Okay. So we decide that in this direction function value decrease. Move along in this direction until you find a minimum there. Stop there. You repeat the process and try to get there. This is what the basic idea of this iterative method. Okay. Sometime we'll see some method the starting point has to be closer for the method to work. So the question is how to find the direction where function value decrease. That's one question you want to answer that. Second one, how far you can move in that direction while minimizing the function value. Two basic questions need to be answered here. find the direction where function value decrease. Second, you want to minimize and find the local minimum in that direction. So these are the two basic questions we're going to look at. That will give you, so the basic differences between different algorithms in the way in which the direction is chosen. Okay? And also sometimes this the minimization on the line as well. So let's look at that closely. So that's what I explained here. One starts at the initial point, determines according to a fixed rule a direction of movement, and then moves in that direction to a local minimum of the objective function fx on that line. You see that you need to solve a one-dimensional problem if you want to find a solution in the direction. So that's a one-dimensional problem. So at the new point, new direction is determined, and the process is repeated. So repeatedly, you do this calculation until you are satisfied that point is pretty close to the solution. So that's how the method works. So pretty straightforward scheme here. All right. So given xk, we need to determine a direction of movement. That's called the search direction. Okay, search direction that generates. Then we generate a point xk plus 1. So we add the point xk. We want to find a point xk plus 1, and using this direction sk, the function value at this xk plus 1 is smaller than the function value xk. Obviously, we are minimizing it, right? And this alpha k is called the step length. That goes how far you can move in that direction. Okay. So two things here. You need to find the search direction. That's sk, and step length alpha k. That's the minimum. So this gives you any point at a point xk plus alpha sk tells you the points on the direction sk. Alpha is positive, you go in this direction. Alpha is negative, go backwards. Okay. The primary differences between different iterative scheme rest with the rule by which successive direction of movement are selected. So depending on what rule you use to define the search direction, we end up getting different methods. Okay, so here are the basic questions. How do we determine direction of movement sk in general? That's one. Second, suppose we know the direction of movement sk, how to determine the step length? So we want to know the minimizer in that direction alpha k, in the direction sk. We are going to do this calculation many times. So we want to come up with some simple notation. We don't want to write the gradient and the Hessian and so on. So what we're going to do, objective function is fx. The gradient is denoted by little gx. Gradient of fx is denoted by little gx. The gradient at the point xk, g superscript k means the gradient at the point xk, right? This means the gradient at the point xk. That's gxk. So gxk is simply denoted by little g superscript k. So this is the notation we are going to use. And also for the Hessian, the function fx, big gx is called the Hessian of f. At the point xk, gxk. So that means simply we're going to write g superscript k. So that means Hessian evaluated at the point xk. So the Hessian of f evaluated at the point xk is denoted by g superscript k. Okay? Because we need to do the calculation n number of times there. Okay. So let's try to answer the first question, finding the search direction. Obviously, we won't have a descent direction. That means we are minimizing the function, right? The function value should decrease at each iteration. So you're going to look at the descent methods here. So as the problem is to find the local minimizer of fx, the natural condition to impose on the sequence of iterates is fxk plus 1 should be smaller than fxk. So you add the point xk. You want to find a point better than that. That means the function value at the new point xk plus 1 should be smaller than the function value at fxk. Okay, that's obvious restriction we need to have for a minimization problem. And so how do you guarantee that at the new point xk plus 1, the function value is smaller than fxk. So a method which generates a sequence of point xk, so that satisfies this condition, fxk plus 1 is strictly less than fxk for every k, is referred to the descent method. Function value decreases. The function value is reduced at each iteration. So we're going to, most of the methods here are descent method because they are minimizing the objective function. So one way of achieving this is to ensure that on each iteration, the search direction sk is a descent direction. Okay? So how do we do that? Look at that. A point xk, so we had a point xk, right, at the approximation to the solution. A direction sk is called the descent direction of gk transpose sk. That means gk transpose means gradient of fxk transpose sk is less than 0. Okay? Then you can show that the function value decreases from using calculus. For sk is a descent direction, and then for small alpha, fxk plus alpha sk minus is less than fxk. You can easily see that if you bring this term to the left, fxk plus alpha sk minus fxk should be less than 0, right? The divide by alpha, fxk plus alpha sk minus fxk over alpha, alpha is positive, and alpha goes to 0, so you have a derivative here, right? So that's what the derivative comes in the direction sk. That's the directional derivative should be less than 0. The slope is negative, the function value decreases, right? So that's the property we are using. And for the vector situation, the gradient times sk should be less than 0. So that guarantees the function value at this point, xk plus alpha sk, alpha positive, is smaller than fxk. So that's called call the descent direction. Descent direction means when you multiply by the gradient vector at the point, it should be negative, strictly negative. Why? I just explained why. Okay, here's the explanation as well. It's easy to see in a one variable case. You can see the slope is negative, function value decreases, right? In a higher dimension, you have to do several variable calculus. So let me show you that the calculation here. It's not straightforward function of n variable. So first we want to show the derivative actually equals to this. The alpha is the variable here. Xk is given. Given estimate at the kth iteration. Sk is the search direction that's given. Alpha is a variable. So you differentiate that, you get this. I think the proof is there. Not sure it's there here or not. Okay, so let's remember f is a function of n variable. F is a function of n variable. Xk is fixed, but here alpha is a scalar. So xk means x1k up to xnk as n component. And the search direction also n component. Right? In 2 dimensions, you have 2 directions. In 3 dimensions, 3, and so on. So sk equals s1k up to snk. N components there. So if you look at the xk plus alpha sk, that means you add component wise, right? You multiply by alpha 1. That means xik plus alpha sik is the ith component. The first one, x1k plus alpha s1k. This one, xnk plus alpha snk. So that's the xk plus alpha sk. So that is any line passing through the point xk in the direction sk is given by this as alpha changes. Alpha is 0, you get the initial point xk. And alpha increases, you get all the points in the positive direction if alpha is positive. Okay, here's the calculation for the derivative in the n-dimensional case. So maybe I'll give you an example in two-dimensional in a minute. Let's go through this. When you differentiate this, you have to apply the chain rule for differentiation. You are differentiating with respect to alpha. Alpha is the variable. So you have the components there, x1, k to the alpha, x. Each component depends on alpha, right? So that gives you partial derivative with respect to x1, evaluated at this point, then differentiate with respect to alpha, that component there. And you have n component, you have sum here. So that gives you, that one when you differentiate with respect to alpha, you get S1k. Remember that is x1k plus alpha S1k. So that gives you, when you differentiate it, you get S1k. So you have S1k up to Snk, that gives you the scalar product. That's the gradient, the component of the gradient vector, partial derivative with respect to x1, partial derivative with respect to x1, evaluated at this point. That gives you this expression here, the scalar product. So that's how the derivative is calculated. So that means this formula is proved like this. So that the gradient evaluated xk plus alpha sk transpose sk. Maybe we want to look at an example to understand this calculation because this n-dimensional case can be difficult to see. I'm going to give you a little example. This is how this can be calculated. Okay. So let's do an example in two variables. Here's the function. Two variables, x1 squared plus 10 x2 squared. The initial point x1 is 1, 1/10. The search direction s1 is 0, -1. So you want to verify this formula. That's the formula I proved in the n-dimensional case. That when you differentiate this with respect to alpha, you get the gradient evaluated x1 plus alpha s1 times s1. That's what we proved. So we're going to check that it's correct here. So the x1 is given, s1 is given, right? So let's call L alpha equals fx1 plus alpha s1. Okay? So I call it L alpha. What is x1 plus alpha s1? So let's write it out. x1 is a vector, s1 is a vector. x1 is 1, 1/10, right? Two components. Plus alpha times s1 is 0, -1. Okay? You add the component wise. That is 1 plus alpha times 0, that is 0, plus 1/10 minus alpha. So that gives you 1, 1/10 minus alpha. Okay? That fx1, all right. Now you can calculate the L alpha. L alpha is f x1 plus alpha s1, right? So that one, f of x1 plus alpha is 1, 1/10 minus alpha. Okay? So fx is x1 squared plus 10 x2 squared, right? The first component. So that gives you 1 squared plus 10 times 1 on 10 minus alpha squared. Substituting the objective, the function fx there. So that's simply a function of one variable, right? You can differentiate that. So dd alpha, so L prime alpha equals dd alpha of fx1 plus alpha s1, which you can calculate that. Just differentiate this. 20 times 1/10 minus alpha times -1, right? Minus 20 times 1/10 minus alpha. All right. So now calculate the right-hand side. That's left-hand side, right? So right-hand side, gx1 plus alpha s1 times transpose s1. So this means gradient. Gradient calculated at x1 plus alpha s1 transpose s1. And that comes down to, what's the gradient? The gradient of fx. Gradient of fx is partial 2x1, 20x2. Okay? And x1 plus alpha s1, we calculated that, which is 1, 110 minus alpha. You substitute it in. So gradient of x1 plus alpha s1 equals 2 times 1, 20 times 110 minus alpha. Okay? So that gives you 22 over 2 minus 20 alpha. Okay? You want to multiply this by transpose S1. That's the transpose, 2 minus 20 alpha. S1 is 0 minus 1. So that is minus 2 times 20 alpha. So that's minus 2 plus 2 alpha. So that's actually the same as L prime alpha equals TD alpha over fx1 plus alpha s1. That's the left-hand side. All right. So you can. So that's the one. When you write it out in terms of alpha, just a function of one variable in this case, and then the normal differentiation. So this calculation expanded to n variables in the previous formula. That's what was done there. But this kind of calculation has to be done all the time when we trying to find the solution. Okay, so that's the basic calculation there. So we want to come up with the method. So we have basically we have answered the question about finding a direction where function value is reduced, right? I'm going to go back to the slide here. All right, that's the formula. We have seen how that formula works. That means when you differentiate this, you get this. We will see the importance of this equality later on. Okay, so we're going to apply this condition here. When you apply alpha equals 0 in the previous formula, d alpha of fxk plus alpha sk, when evaluated at alpha equals 0, you get gxk transpose sk. Okay, gxk transpose sk. It's less than 0 because the search direction is a descent direction, means it should be product should be less than 0. So that means if this is true, then function value will be reduced. Fxk plus alpha sk is less than fxk for small alpha. Okay, alpha is small, the function value is reduced from this calculation there. Okay, that answers about the direction, how we find the search direction with function value reduced. The second question we want to know here, how we find the local minimum along this direction. So let's go to the line search. So if you say continuously differentiable function, the process of determining a minimizer on a given line is called the line search. Okay, we know the direction in which function value decreases. We want to move along this direction until we find the local minimum. Okay, so you want to solve that one-dimensional minimization problem. The process of finding a minimizer on a given line is called the line search. That's this minimization. So fxk plus alpha sk. So that's the search direction. So we want to minimize this function, alpha bigger than or equal to 0. That gives you the point where the minimum point is where we move up to that point. Sk is the search direction, xk is the estimate. So you see that it's a function of one variable. So each step you have to solve this problem efficiently. Alpha is the variable, the xk is given, sk is given. That's Sk is the estimate, Sk is the search direction. So let's say Sk is the descent direction. Then the necessary condition for alpha k to minimize that, how do you find the minimizer? You want to differentiate this with respect to alpha and make it equal to 0, right? That's the stationary point. If alpha is positive, that's a minimizer, all right? So when you differentiate it, you get this condition. Gxk plus alpha k sk transpose sk equal to 0. Then alpha k will minimize this. So this is called the line search condition. That's what we derived before, the derivative of that. What happens if we don't evaluate the function with respect to alpha and differentiate it? That's inefficient because at each step you had to calculate the gradient. So you use the gradient to calculate the derivative. Gxk plus alpha k sk times sk. We don't work with the objective function because you use the gradient to find the search direction. We use that information repeatedly. So that's the efficient way of doing that. So that's how we develop this formula. Gxk plus alpha sk times sk equal to 0. That's the necessary condition that minimize this function. So that alpha k is called the step length. I think it's there. The reason is if sk is the descent direction for small alpha, fxk plus alpha sk is stick less than fxk for alpha k positive. And then we find a minimizer alpha k. That's a one-dimensional problem. Alpha bigger than or equal to 0. Alpha k cannot be active, right? So alpha has to be positive. Alpha is active, then you stay at the point. Alpha equals 0. That's not good. So that's a necessary condition. You can check the second derivative, see that's a minimizer or not. And then you solve this to find minimizer. I think now, so we know how to find the step length. We know how to find the search direction. So we are now ready to define a method. Before, I think I won't start it here today. So just to give you a geometric interpretation of this, this means these two vectors are orthogonal. Gxk plus alpha k sk transpose sk equals 0. The line search condition gives you the search direction is orthogonal to the new point. Sk is the search direction, and this is the new point. They are perpendicular. Okay? The search direction sk is tangential to the contour of the point passing through the point xk plus alpha k sk. So that's a geometric interpretation of that. So I'm going to stop with this. So next week, not next week, we don't have lectures in week 6, right? It's tutorial only. We'll talk about the steepest descent method and so on. Okay? So we just looked at the basic ideas involved in that. Okay, so I stopped with this today. Then we look at the algorithms and so on.